Well, hi guys. This time we're going to have a look at the Victorian VCAA 2014 chemistry exam, and specifically I'd like to look at the multiple choice section of the exam, and I propose to do this in two parts. Part 1 will be questions 1 to 15 and part 2 would be questions 16 to 30. So let's have a go and see what we can find out. Question 1. The expression for the equilibrium constant for the reverse reaction of this little beastie here would be, okay, nice easy question guys, these would be the products of the reverse reaction, would they not? And therefore look for something with H2O concentration squared and CH4 on the numerator, which would be this one, wouldn't it be? I think so, and therefore the answer would be number A. Today, hooray for number A, and let's look at number 2. If an inert gas is added to the equilibrium mixture of the question we've just been dealing with at a constant temperature and a constant volume, the concentration of a hydrogen would, well guys, don't fall for that one, because none of the concentrations of the individual reaction components, that is measured as their partial pressures, there should be a closed bracket after partial pressures, will be altered by the introduction of the inert gas. No equilibrium position shift is required and none will eventuate, okay? Hence the concentration of the hydrogen and, for that matter, all other components remains constant, okay? So the answer is going to be C, okay? Did you know that? Inert gases don't change anything, guys. Alright, question 3. This one's a favourite trick question, but we won't fall for it, guys. Which of the following statements about 10 mils of 0.1 molar hydrochloric acid and 10 mils of 0.1 molar ethanoic acid solution is true? Okay, well, students look at this and they say, well, goodness, this is a strong acid, this is a weak acid, so, and then they fall right into the trap. So let's go through the alternatives. Alright, each solution will have the same electrical conductivity. That's not true. Alright, part B, that is actually true, and I'll explain that in a moment. Each solution will react completely with 10 mils of 0.1 molar NaOH solution. Shock horror, yes, it is true. Even though one's a strong acid and one's a weak acid, it's true. Part C, each solution will react at the same rate with 1 gram of magnesium ribbon. Absolutely false, because the concentration of the products of the dissociation of both acids are quite different, and this is crucially important because remember the reaction that you have when a metal reacts with an acid. It's metal plus acid gives salt plus hydrogen, and what happens is it's the products of the dissociation of the acid, in particular the H plus ions, which are reacting with the, in this case, the magnesium ribbon. So the metal is oxidized and the H pluses are reduced to hydrogen in what is a redox reaction. So obviously guys, the H pluses in contact with the magnesium is where the action is for the redox to occur, and the higher the concentration of H plus ions, as you will get for an HCl acid solution, then the faster the rate of reaction. So they cannot be having the same rate of reaction, and therefore this one's false. And D, the concentration of H3O plus ions will be greater for the ethanoic acid solution. What a load of rubbish. That's a weak acid. HCl is a strong acid, therefore the concentration of H3O ions will be greater in the hydrochloric acid. Okay, so that's wrong. Now guys, why is B correct? Well, B is correct for the following reason. You get this reaction happening with the ethanoic acid, and this is the dissociation reaction here, and you've also got the equilibrium reaction for water happening here, such that this plus this gives this, and it's an equilibrium reaction, and at 25 degrees Celsius the concentration of this beastie times the concentration of that beastie has to be exactly 10 to the minus 14. Now, what happens guys, even though ethanoic acid is a weak acid, what will happen is when you start introducing OH minus ions into here, as is proposed in option B, what will happen is the OHs will react with these and will use them up, okay, because they're electrostatically attracted to each other. This in turn disrupts the equilibrium reaction here and forces it further to the right to make up some more of these. So what happens is, as you progressively add OH minuses, they react with these beasties, using them up, which forces the reaction to the right further and further and further and further and further till the entire amount of ethanoic acid has been used up. So even though it's only a weak acid, and you might say, well, it doesn't dissociate as much as the HCl because it's a weak acid, makes no difference, guys. It's all about equilibrium. And if you disrupt the equilibrium, you'll keep on forcing the reaction to the right, to the right, and to the right, and to the right, until every single skerrick of this has been used up anyway, just as is also the case with the HCl. So option B is correct. Okay, guys? Question 4 now. If solution X has a pH of 3 and solution Y has a pH of 6, then we conclude that. Alright, let's have a look. Option A is looking pretty good to me. That looks excellent. If for solution X the pH is 3, that means that the concentration of hydronium ions, aqueous hydronium ions, is 10 to the minus 3. And for solution Y, if the pH is 6, it follows that the concentration of hydronium ions is 10 to the minus 6, okay? So that's how pH works, guys. So therefore, this is correct, definitely, because that is 1,000 times that, okay? Now look at this. If solution X is half, no, that's rubbish. It's not half. 3 is half of 6, but it's a logarithmic scale, guys. So that's not correct. OH, the concentration of OH in solution Y is twice that. That's also rubbish for the same reason. Option D, solution Y must contain a stronger acid than solution X. Well, that's ridiculous, because as the pH goes up, it's a weaker acid. So, you know, these are obviously all wrong, and option A is correct, guys. Alright, now question 5. The pH of the following acid solutions was measured with a pH meter. We've got all of these: nitrous, ethanoic, hyperbromous, hypochlorous. Okay, what's all this? The volume, okay, and the concentration. Concentrations are all the same. Okie dokie. So the acid solution with the lowest pH, that means the strongest acid, doesn't it? Well, I think we need to consult our trusty data book and look up the Ka's, because that'll tell us which is the strongest and which is the weakest. So if we look those up, we get nitrous as that, we get ethanoic as that, we get hyperbromous is that, and we get hypochlorous is that. Now, remembering, guys, we're looking for the strongest acid, that is with the highest level of dissociation, and therefore the highest Ka. And remembering, the highest Ka is the one here, this one, where this number, this index, the actual value here is lower, because a lower number there means a higher value. You understand? 10 to the minus 4 is 1 over 10 to the 4. So I would be saying that it's going to be nitrous. So lowest pH is the strongest acid, highest Ka, nitrous acid, so the answer is A. Today, hooray! Alright, question 6. The diagram below represents the titration curve for the reaction between a particular acid and a particular base. The equation that best represents the reaction described by the titration curve is... Alright, guys, if we look at this curve here, what we notice is that the equivalence point is in the acid region. Okay, that's very important, because that probably indicates to us strong acid, weak base. Okay. Also, we're noticing that up here we have not got a very robust behaviour of the pH there. This is basically being fairly easily wounded, if you like. The curve is coming down pretty easily, okay? So for a strong acid, strong base, you'd get sort of pretty well horizontal and then just giving up at the last minute, like that. This one's not like that. So to me, we're making the solution increasingly acid. This is the base isn't holding up too well. Weak base, strong acid, I'd say. So let's look at the options. So in option A, we've got a strong acid and a weak base, which I think is exactly what we're after, isn't it? So that's looking pretty good. We've got strong base, strong acid in that one, no good. We've got weak and weak in that one, and in the last one we've got weak acid, strong base, which is what we don't want. So obviously we want option A. Hooray for option A. Question 7 for us now. What volume of 0.25 molar hydrochloric acid is required to react completely with 40 mils of 0.5 molar calcium hydroxide? I think an equation is required here, guys. Yes. Okay, so we can see that you've got 2 moles of the hydrochloric reacting with 1 mole of the calcium hydroxide once it's stoichiometrically balanced. Okay, so alright, now the number of moles of calcium hydroxide is 40 thousandths times 0.5 moles per litre, which gets us 0.020 moles. Therefore the moles of hydrochloric acid is exactly twice that, which is 0.040 moles. Therefore the V of hydrochloric acid over 1,000 times 0.25 moles per litre concentration of the hydrochloric acid gets us 0.04. Solving for V, we get that, which is 160, which looks like option D. Okay, great. Alright, what have we got? Some hydrochloric acid is added to aluminium sulfide, and when that happens, the highly toxic gas hydrogen sulfide, which is rotten egg gas, is evolved. The equation for this reaction is, alright, feast our beady eyes upon it. So if excess hydrochloric acid is added to 0.2 moles of aluminium sulfide, this beastie here, then the volume of hydrogen sulfide produced at SLC will be, alright, that's a pretty straightforward question. This produces 3 times the molar amount of this. So if we've got 0.200 moles of aluminium sulfide, guys, then we're going to have 3 times that much of hydrogen sulfide gas, which would be 0.600 moles, and we've got PV equals nRT. We're going to solve it for V, don't we? The volume. Okay, so therefore V is nRT over P. We've got N is 0.600, R is 8.31, T is in Kelvin, 298, which is SLC temperature, and 101.3 is the pressure at standard laboratory conditions, which will get us, okay, that'll get us 14.7 litres. The answer looks like this one, guys. The answer looks like that one, D, for you and me. Okay, over the screen we go. Question 9. An aerosol can with a volume of 300 mils contains 2.80 grams of propane gas as a propellant. The warning label says that the aerosol may explode at temperatures above 60 degrees Celsius. What is the pressure in the can at a temperature of 60 degrees Celsius? Well, that's just a case of good old PV equals nRT again, I think, solving for P. So we've got PV equals nRT. We know that therefore P will be nRT over V, where N is 2.8 grams divided by the molecular weight of propane, C3H8, 12 threes, 36 for the carbon plus 8 for the hydrogens, and T is 273 plus 60, which gets us 333 degrees Kelvin, and V is 300 thousandths of a litre. You've got to make sure your units are all consistent for use of your PV equals nRT equation. So now we just plug and play, guys, I think. P is going to be, okay, 2.844ths of a mole of propane times 8.31 times 333 times, oh, that's over V, so it's 300 thousandths, and let's see what we get for our pressure, guys. 587, which looks like option C for you and me. Great. Okay, question 10. Which of the reactions of hydrochloric acid below is a redox reaction, guys? Redox. Oxidation number time. Let's go for it. We've got hydrogen is +1 here and 0 here. So that's been, the HCl has been reduced. Okay, that's what you say there. The HCl has been reduced, but the oxidation numbers of the hydrogen tell the story. And, ooh, that's going from 0 up to +2. That's a redox reaction if ever I saw one, guys. Very good. Let's check the others now. Hydrogen hasn't changed in option B. Chlorine hasn't changed in option B. Sodium hasn't changed. No. And the sulfur hasn't changed. No way, Jose. Option C. Okay, hydrogens have not changed. Chlorine hasn't changed. Magnesium hasn't changed, and the oxygen hasn't changed. Nope, no way, Jose. Option D, hydrogen has not changed. Chlorine hasn't changed, that's right. Potassium hasn't changed. Oxygen hasn't changed, and carbon hasn't changed either. Well, that's not a redox either, so it's option A. Hooray for option A. Okay, question 11. Consider the following unbalanced ionic equation where we've got mercury, liquid mercury plus dichromate plus this equals this plus this plus this. Alright, redox guys, and it's unbalanced. So let's go through the motions. The dichromate is being reduced to Cr3+, so let's do that first and then we'll do the oxidation of the mercury second and we'll balance it all up. Now the first thing we've got to take note of is that there's got to be 2 of these chromium 3 pluses, because that's no good. You've got to have it stoichiometrically balanced, okay? That's the first thing. Now you know the rules for dealing with polyatomic ion redox. This is a polyatomic ion beastie. The first thing you do in an acidic environment is you take note of the oxygens and balance them with water. So you must add 7 waters there. Okay, so that takes care of the oxygen, but now it's throwing the hydrogens out. So then you balance the hydrogens with H pluses on the other side. That gets us 14 H pluses, and then lastly, you know what to do. You balance the electrons for the charge. So what do we got? Come on. 14 minus 2 is 12. 12 pluses on this side. 6 pluses on this side. So we've got to add 6 electrons over there. Good show. Now let's do the mercury now. We've got Hg liquid going to Hg2 plus aqueous. Alright, so this is getting oxidized. We'll put 2 electrons over here to balance the charge. Now, if we were to combine that into the overall equation, as we are aiming to do, we would note that there are 6 electrons here and only 2 there, so that's no good. That's not going to balance if we try to combine them into an overall equation, because we need the electrons to cancel each other out on each side. So we'll multiply this whole mercury thing by 3, okay? So what do we get? We get 3 of those, 3 of these, and not 2 but 6 of those. So you can see the answer to our question now, guys. We need 3 of these beasties, so it's going to be C. So there's your overall. I've done it for you, and you will notice that the electrons have cancelled each other out, and we've got a beautifully balanced stoichiometric little masterpiece, and the answer to our question is C for you and me. Yippee! Okay, question 12. 4 straight chain alkanols S, T, U and V with general formula R being the alkyl group OH were analysed using a gas chromatograph combined with a mass spectrometer. The following chromatogram was produced. Okay, so we've got that thing there. Now, the order of the alkanols from the highest molar mass to the lowest molar mass, easy as, guys. You know that the dispersion forces are higher for the higher molecular weight molecules, and therefore they result in longer retention times. So this beastie has the highest molecular weight, that one has the lowest molecular weight. Therefore, in order, now which order have we got to do this? In order from the highest molar mass to the lowest will be V, there at the highest end, then U, then T, then S, which looks like option A to me, doesn't it? Great. Question 13. Now we're still dealing with that same situation there with the mass spec being step 2 of the process after the gas chromatograph. So the mass spectrum of alkanol T is provided below. Okay, what is alkanol T? Well, guys, easy as again. There is the mass of the parent ion. It's got a 60 mass molecular weight of the parent ion. So therefore, it helps to know that basically the formula for alkanols is same as for straight chain hydrocarbons, except that there's an O there in the mix as well. So therefore it's very easy to work out. CnH2n plus 2O, and we just go like this. Therefore 12 times N being for the carbon plus 2N being for the hydrogen plus another 2, that's 2N plus 2 hydrogens I mean, plus 16 for the 1 oxygen equals 60, and just solve it for N. So you've got 14N plus 18 equals 60, therefore 14 equals 42, N equals 3, and therefore we're looking at propan 1-ol. That was pretty easy, wasn't it? So remember our little formula for alkanols. This one here really helps, okay? Alright, question 14. A thin layer chromatography TLC plate was set up with a non-polar solvent, hexane, and a polar stationary phase, silica gel. Okay, the chromatogram below was obtained. The ruler has been placed next to the plate. The RF value for the compound would be. Okay, this is a little bit tricky, guys, because the origin is not at 0. Tricky, tricky, tricky. So let's work it out and not be tricked. We can say that that's our origin there at 2. That's where the compound is currently sitting, and the solvent front got as far as 20. Therefore, the RF would be 16 minus 2 over 20 minus 2, 2 being our baseline, our origin, and work that out. That's 14 over 18, which is 7 over 9, which is 0.7 repeating. By the way, did you know that 1 over 9 is 0.1 repeating, 2 over 9 is 0.2 repeating, 3 over 9 is 0.3 repeating, and so on and so on and so on. And 8 over 9 is 0.8 repeating. Okay, so this one is 0.7 repeating, which looks like the answer is B. Alright, last question for this video, question 15. Looks like the dreaded NMR, guys. Alright, so let's have a look at this. What have we got here? TMS, and we've got 3 different peaks, 3 different environments for carbon-13. Okay, this is carbon-13. So we're looking for 3 different carbon environments, I presume, and we're going to work out which of these molecules is the correct one. Yes, alright, so let's look at them in turn, and being very careful as we go. 13 carbon NMR. So, alright, let's do the first one. Now, that's, what is that? Propane. This guy on the ends, he's exactly the same thing from the other side, like a mirror image, but he sees the same neighbourhood as this guy does, okay? So therefore, there is a line of symmetry down the middle, and there's only 2 carbon environments, so that's no good. We need 3. Let's do option B now. Option B is 3-methylbutane. Alright, so 3-methylbutane, have I got this right? That could be 1, 2, 3, and there's your methyl. Now, look for the symmetry line. So this beastie here and this beastie there, they both see exactly the same rest of the molecule. Okay? See? You see that? Look. So they have the same rest of the carbon environment. Okay? So there's one effective carbon environment for those 2 molecules, the same neighbourhood. Then you've got 2, and then 3, and then 4. So it looks like there's 4 different carbon neighbourhoods. B is no good. So let's go to C now. What is C? 2-methylpropan-1-ol, and D looks like 2-methylpropan-2-ol. Alright, so let's see if one of those gives us some joy. There's C. So 2-methylpropan-1-ol, there's your 1 there. Okay, so what am I seeing? I'm seeing a symmetry between this one and this one, a line of symmetry going right down there, like that. So therefore, there's one environment here, and here they're both environment 1, environment 2, environment 3. This looks like this could be our winner. Let's just do D to make sure, but I think C might be the one we're looking for. Now, D is, right, what is it? 2-methylpropan-2-ol, so the ol is on the 2, okay? Now, how many environments have you got there, guys? How many carbon environments? Well, have a jolly good look at it, because this beastie and this beastie and this beastie all see the same rest of the neighbourhood. They see, you see, they're all hooked onto a central carbon atom here, and they basically all see the same thing in terms of the rest of the molecule. You have a look at it. You see, look, you've got this environment here is the same as this environment here, because they're all hooking onto a central carbon atom with 2 other groups the same. Okay, whichever way you look at it. Okay, this one here is hooked onto the same central carbon with 2 other methyl groups, if you like, to look at, which are hooked on also to the same central carbon atom. And remember, all these things are in 3D. See, so this guy sees the same thing in space as this guy does, So this has really only got 2 different carbon environments, and therefore C is our answer. Okay? Alright, well, we'll see you soon for part 2.